Today I want to look at a nice relationship between Mersenne primes and the sum of divisors function. But let's recall what those are first. So a prime is called a Mersenne prime if it's of the form 2 to the m minus 1. And so these are maybe the most popular type of primes. And in fact, I think the largest known prime is a Mersenne prime. There's a big internet search for Mersenne primes. And then the sum of divisors function, well, it's aptly named. That just gives you the sum of divisors of n, and it's denoted sigma of n. Now, I'd like to start with an observation that we're going to sketch a proof of, and that is, if we've got a prime factorization of n as p1 to the r1 up to pk to the rk, where those pi's are distinct primes, then sigma of n can be written as the following product. We've got p1 to the r1 plus 1 minus 1 over p1 minus 1, and then the product of things like that up to p sub k to the rk plus 1 minus 1 over p sub k minus 1. So like I said, I'm really going to do a sketch of a proof here. So here I say I have proof, but this is really just a sketch of a proof. And I'm going to sketch this proof in two cases. So my first case will be the case if n is simply the power of a prime. So let's say that n is equal to p to the r. But now let's look at the divisors of n. And the divisors of n are simply 1, p to the first power, p squared, all the way up to p to the r. So they're just powers of that prime. Nothing else will divide p to the r just based off the fact that we're working with a prime there. But now let's observe that we can take sigma of n, and we'll just simply get this sum 1 plus p squared all the way up to p to the r. But that's the sum of a finite geometric series. That just gives us p to the r plus 1 minus 1 over p minus 1. And so that would be like the k equals 1 case of this observation. Now let's look at our second case here, which will be the last case that I do in this sketch of the proof. And that is if we have n is equal to, perhaps we'll say p1 to the r1 times p2 to the r2, and p1 and p2 are distinct. So in other words, it's the product of powers of two distinct primes. But now what I'd like to do is lay out the divisors of this, and I'm going to lay out the divisors of this in an array instead of in a line. So I'll have 1, and then p1, and then p1 squared, all the way up to p1 to the r1. So we want to read this as all of the divisors that are not multiples of p2. And then down here we'll have p sub 2, and then p1 times p sub 2, and then p1 squared times p sub 2, all the way up to p1 to the r1 times p sub 2. So that's going to be all of them that are a multiple of p sub 2, but not p sub 2 squared. And then we're going to go all the way down here. We'll have p sub 2 to the r sub 2, and then p1 times p sub 2 to the r sub 2, all the way up here to p1 to the r1 times p2 to the r sub 2. Great. But now what we'll do is sum along each of these lines here, using the fact that we've got a finite geometric series for each of those lines. We just have a different starting term. So the starting term here is 1, so we simply get p to the r1 plus 1 minus 1 over p minus 1. And here the starting term is p sub 2. So we're just going to get that object again times p sub 2. So where should I put that? Maybe we'll have this as p1 to the r1 plus 1 minus 1 over p1 minus 1 all times p sub 2. And then we go down here to this last one, and that's going to give us p1 to the r1 plus 1 minus 1 over p1 minus 1 times p sub 2 to the r sub 2. But now what we'll do is we'll sum down this vertical line, keeping in mind now we've got a finite geometric series where the starting term is this fraction here, and the common ratio is p sub 2. And so putting all that together, we'll see that sigma of n is exactly what we want it to be. So it'll be p1 to the r1 plus 1 minus 1 over p1 minus 1 times P2 to the R2 plus 1 minus 1 over P2 minus 1. And then, as you can imagine, we could just inductively proceed and end with this final formula here. Maybe I'll leave that to you in order to do that. Okay, so now that we've got this setup of this nice formula, if you will, for sigma of n, let's look at the main result that will tie these two things together. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up. And if you're not yet subscribed, consider subscribing. It really helps out. Okay, so the main proof that we want to look at here, or the main result we'd like to prove, is that sigma of n is a power of 2 if and only if n is the product of distinct Mersenne primes. So in other words, all its prime factors are Mersenne primes, and they don't appear with an exponent larger than 1. And now we're going to proceed by induction on the number of prime factors. And so I guess our base case could be 0 prime factors. In other words, we have the number 1, but the sum of the divisors of 1 is just 1, which is 2 to the 0. Well, that does an alternative base case, but I think this base case is a little bit more illuminating. And so our base case is n has a single Mersenne prime factor. In other words, it is a Mersenne prime. So it's of the form 2 to the m minus 1, which is prime. But now let's observe that we can write sigma of n as 1 plus n, right? Because if n is prime, it only has two divisors, 1 and itself. But we know that that's 1 plus 2 to the m minus 1 because n is a Mersenne prime, so that gives us 2 to the m. In other words, we've got sigma of n is a power of 2. Now, if you'd like to sketch out what happens if you have two Mersenne prime factors, that might be an interesting thing to do as well. So let's say that n is equal to 2 to the r minus 1 times 2 to the s minus 1, both of which are prime. But notice that that means that sigma of n is going to be 1 plus 2 to the r minus 1 plus 2 to the s minus 1, and then plus itself. So it's going to be 1, that's one of the divisors. 2 to the r minus 1 is one of the prime divisors, and 2 to the s minus 1 is the other prime divisor, and then you've got n, which divides itself. But now let's observe that this is going to simplify as follows. We'll have 1 minus 1 is 0, so we'll have 2 to the r plus 2 to the s minus 1 plus n, but we can multiply n out to 2 to the r plus s, and then we'll have minus 2 to the r minus 2 to the s plus 1. But let's observe that this 2 to the r will cancel with this 2 to the r. This 2 to the s will cancel with this 2 to the s. That s should have been in the exponent. And then this number 1 cancels with this number 1, leaving us with 2 to the r plus s. So that actually kind of illuminates what's going to go on, because let's observe that that power of 2 that we actually get is the sum of the powers of 2 that are inside those Mersenne primes. So perhaps we should be on the lookout for that kind of thing happening when we do our induction step. Okay, nice. So now what I'd like to do is suppose the statement is true. So this is going to be our induction hypothesis. So I'll just say the statement is true for all n with k such prime factors. So what do I mean by k such prime factors? I mean that n, or all integers of the form where they factor as k distinct Mersenne primes. And then let's consider the number n, which is, maybe I should say for all n not with k such prime factors, just so I don't like reuse my n. So let's consider n to be p1 times p2 all the way up to pk times pk plus 1. But now I can write that as n naught times pk plus 1. And let's observe the following. So n naught will be considered via the induction hypothesis. So I'll just put a little arrow there to say that the induction hypothesis applies to n naught because it's the product of k distinct Mersenne primes, and then pk plus 1 is of the form 2 to the m minus 1, because we're assuming that all of those are Mersenne primes. But now let's observe that we can write sigma of n in the following way. So that's going to be sigma of n naught times p sub k plus 1. But then that's going to be the sum of divisors of n naught plus p sub k plus 1 times the sum of divisors of n naught. And that's because we can simply partition the divisors of n into the divisors of n naught plus p sub k plus 1 times the divisors of n naught. So in other words, it's the divisors of n that are multiples of pk plus 1 and the ones that are not multiples of pk plus 1. But now let's observe that that's going to give us sigma n naught plus pk plus 1 is of the form 2 to the m minus 1. And then we've got sigma n naught there. But when all is said and done, we get 2 to the m times sigma n naught. But now we can apply the induction hypothesis to sigma n naught to say that sigma n naught is a power of 2. So that's this suppose the statement is true business here. So let's replace that with a power of 2, and we'll have 2 to the m plus n after putting those two things together. Okay, so that's how this, let's see, that's going to be the reverse direction. So let's just point out that we did the reverse direction. Now let's look at the forward direction of this statement. Okay, so we just finished this reverse direction, that if n is the product of distinct Mersenne primes, then sigma of n is 2 to the n. Now we'll do the forward direction. So let's suppose that sigma of n is equal to 2 to the n. It's a power of 2. And let's suppose that n is equal to p1 to the r1 multiplied up all the way up to pk to the rk. So in other words, it's of this form right here. And so now what we'd like to show is that each of those pi's are Mersenne primes, and we'd like to show that each of those r sub i's are just the number 1. Okay, so let's observe we have the following equation. So we have 2 to the n is equal to sigma of n, which is equal to this p1 to the r1 plus 1 minus 1 over p1 minus 1 multiplied all the way up to pk to the rk plus 1 minus 1 over pk minus 1, just by our little observation down here. But now let's observe that this left-hand side is a power of 2, and then we've got a product of natural numbers over there on the right-hand side. That means each of these natural numbers is a power of 2. So this thing right here is equal to 2 to the m1, for instance. This thing down here is equal to 2 to the mk, for instance. So, and they're not just powers of 2, there are powers of 2 that are bigger than 1. I'll let you think about why we know they are not 2 to the 0, that they have to be at least 2 to the 1 or 2 to the 2, or anyway, powers of 2 that are not equal to 1, but suffice it to say they are. Okay, so now let's pick one of these kind of at random and show if we have an object like that as a power of 2, then the prime associated to that object is a Mersenne prime, and the exponent associated to that object is equal to 1. So let's just maybe point out that that's what we're doing right here. So suppose we have p a prime, so it's kind of any prime, and r a number bigger than or equal to 1 with, let's see, we need p to the r plus 1 minus 1 over p minus 1 is equal to 2 to the m. So in fact, what we're doing is we're just like looking at each of those green boxes there, but we're like looking at them all at once, and we've removed the index just to make it a little bit neater. But now what I'd like to do is undo some of the work that we did in our original proof over here, and that undoing means I'm going to take this and rewrite it as a geometric series. So we have 1 plus p squared all the way up to p to the r is equal to 2 to the m. Now, let's observe that the right-hand side of that is even, but that means that p has to be an odd prime. So let's write this down. P is odd, Because if p is even, then the left-hand side of that is an odd number. But we know that the left-hand side also has to be odd given that the right-hand side is even. Sorry, the left-hand side has to be even given that the right-hand side is even. Furthermore, if we reduce this thing mod 2, we'll have the following. We'll have r plus 1 is congruent to 0 mod 2. That's because since p is an odd prime, each of those are simply 1 mod p. So we've got 1 plus 1 to the first power plus 1 squared, all the way up to 1 to the r mod 2, but that's just going to give us r plus 1 mod 2, and that's 0 mod 2 because the right-hand side of that is 2, which is even. But observe, that tells us that r is an odd number because r plus 1 must be an even number. So let's write r as 2s minus 1. So we can write odd numbers like that. But now let's observe, that's going to give us the following equation. We'll have 1 plus p squared all the way up to p to the 2s minus 1 is equal to this power of 2. But then from there, we can resum that as a geometric series, giving us p to the 2s minus 1 over p minus 1 is this power of 2. And now let's see what we can do with that. So keeping in mind where we ended up in our previous argument, let's observe that what we need to show to finish this thing off is that if we have an odd prime p and then two natural numbers m and s, satisfying this equation p to the 2s minus 1 over p minus 1 is equal to 2 to the m, then s is equal to 1. S is equal to 1 means our original power of our prime is also equal to 1 because 2 times 1 minus 1 is equal to 1, and p is a Mersenne prime. That's the other thing that we need to end with. Okay, so now what I'd like to do is take this equation that we've built right here and rewrite it a little bit. I can factor this numerator as, let's see, p to the s plus 1, and then p to the s minus 1 over p minus 1. Notice that's just a difference of squares factorization, and then this is 2 to the m. Okay, nice. But now let's observe that we've just factored a power of 2 as the product of two different things, but that means each of those things are powers of 2 as well. So that means that we can write p to the s plus 1 as 2 to the a with a less than or equal to m. That's because the power of a in this factorization can't be bigger than m because it would give us a larger power of 2 than we have over there on the right-hand side of the equation. But now what I'm going to do is replace p to the s with a thing involving this 2 to the a in as many places as possible. So that's going to lead me to the following equation. So we have 2 to the m is equal to 2 to the a, that's p to the s plus 1, and then that's going to be times 2 to the a minus 2 over p minus 1. So this p to the s minus 1 is 2 to the a minus 2, just like subtract 2 from both sides of this equation. I think that's like pretty clear. But now what I'm going to do is I'm going to clear denominators here so we never get worried about things being inside of the integers or not. So let's observe that this pretty quickly turns into the equation 2 to the m times our prime p minus 1 is equal to 2 to the a plus 1 times 2 to the a minus 1 minus 1, after I did a little bit of factoring. So I factored a 2 out of the numerator right there. But now I'd like to observe that this object right here is most definitely an odd number. The only way that it could be even is for it to be equal to 0, but the left-hand side is pretty clearly not equal to 0, meaning that thing is odd. And then this thing right here, this p minus 1 is an even number because let's remember that p was an odd prime. So, well, what does that tell us? Well, notice that we have a power of 2 here, which is capturing the entire power of 2 on the right-hand side. And we've got a power of 2 on the left-hand side that's capturing just part of the power of 2 on the left-hand side. So in other words, we have m is less than a plus 1. Because, like I said, that a plus 1 is capturing the whole power of 2 over here. This is just capturing part of the power of 2. That means we've got this inequality right here. But now let's observe that we can quickly rewrite that as m minus 1 is less than a. But then let's also recall that a was less than or equal to m. So check it out. We've just squeezed a between m minus 1 and m, but it could be equal to m. So that means that we've got a equal to m. Okay, nice. But now what we'll do is plug all of this information up to this equation that I've kind of sloppily underlined in this magenta color. So let's observe that I can replace my p to the s plus 1 with 2 to the m, just based off the fact that a and m are the same now. So we've got 2 to the m times p to the s minus 1 over p minus 1 equals 2 to the m. But that means that p to the s minus 1 over p minus 1 is equal to 1, but that means that s is equal to 1. But then we can take this s being equal to 1 and loop it back into our equation that's right there, and we'll see that we immediately have p is equal to 2 to the a minus 1. In other words, p is a prime of the form 2 to the a minus 1. It's a Mersenne prime. But let's recall that after all of the work we did before, that's all that was left to show to finish this thing off.